Hey friends, we are in chapter 4. We're finishing chapter 4. We're actually in section 4.7, and we're going to talk about some pretty special functions. My guess is this might be 2 sections, so don't be alarmed. I also broke down the vocabulary a little bit differently, so I want you to stay tuned. There's going to be a couple pages of vocabulary. It's not as bad as it seems. I just need the space in order to draw and to show you a little better what I'm talking about. So let's take a look. So there will be 5 vocabulary words. The first 2 are related to one another because they refer to the same concept. This concept that we're going to talk about, the first one is a step function. A step function is a function whose graph consists of a series of line segments. Oftentimes, I'm going to try to draw one here for you really quickly. Oftentimes, a step function, here's an x and y axis, and I'll use red to illustrate. A step function will look something like this. Kind of a little line, open circle at the end, and it looks like, yeah, you guessed it, a step. It can go back, or a pair of stairs, or whatever. All right, so that's what we have. They don't look like lollipops falling down on some, anyway. So that's what a step function looks like, and we'll talk about how we'll use them and why we'll use them. One specific type of step function that we'll talk about is the greatest integer function. It's a function where f of x is equal to the greatest integer less than or equal to x. I always hated greatest integer functions because I hate the way it reads. So let's think about it. Let's read it through again, and I'm going to kind of give you an analogy to kind of think about. And I'll show you actually what it looks like. When it's written down, it's given as f of x is equal to x with like this kind of a bold bracket around it, something like that. Some textbooks use slightly different symbols. Some textbooks also call this a floor function and a ceiling function. We may use that terminology if we graph it using some technology, but we'll talk about that later. Right now, when I'm talking about the greatest integer function, I am talking about if I choose an x value, let's say so let's make a table. So x on one side and f of x on the other. And remember, we are using this funky symbol to define x. So we're going to read the definition every time we put a number in for x. And when you do the greatest integer function, it is good to use numbers that are other than integers, right, for your x value, and you'll see why. So let's start with like 0, right? So if I put 0 here into this function, we don't know what it is, we need to go back and read. A function where f of x, this thing, is equal to the greatest integer less than or equal to x. Okay, integers, Dion told us it was negative and positive whole numbers. So what is the greatest integer equal to or less than 0? Yeah, it's 0, because 0 is an integer. Let's try another number, but let's not go like to 1, 2, and 3. Let's go to like 0.5. Let's go to a half. All right, so what is the greatest integer less than or equal to 0.5 or 0.5? It's still 0. Let's try again. What about 0.75? What is the greatest integer, remember whole number, that's equal to or less than 0.75? It's 0. What about 1? What is the greatest integer that's equal to or less than 1? Well, 1 itself is an integer, so we get a 1 here. Kind of weird, but this is a classic function that we're going to talk about. I'm going to call this the birthday function. Think about it this way. I have 2 kids, well, 2 boys who care about their birthday. My daughter's like, I don't know how old I am. She's 2. But my boys will tell you that they are, well, they would have told you a couple months ago that the youngest would have said that he was 4.5 or 4 3/4 or something like that. But the reality is he's 4. I don't care about that quarter. I don't care about that half. You're 4. Get it? So the point is, even if you are 4 years and super, super close to your birthday, you don't become 5. We don't say that you're 5 until you turn 5. So how does this look in a graph? So in a graph, if I were to graph this, and you'll see that it'll become a step function, let's say the x-axis refers to years, right? And if my child is 1, and then we'll put age over here for the y-axis. So if my child is anywhere from 0 to, so if my child is 0 years old, they're 0 years old, right? Half of a year, still 0, not going up. As soon as my child hits 1 year,
the child is no longer 0 years old. The child is 1. So now I move up. So the age, the official age is 1. So my child is 1.5. So I'm going to put a 1 here so you get what I'm talking about. This is a 2. If my child is 1.5, we still say he's 1. If my child is 1 3/4, you're still 1, pumpkin. But as soon as you have a birthday, I'm not going to call you 1 anymore. Pop, your age is going to be 2. Get it? So you go up to 2 here. Right? So here what I'm creating is this step function. We're going to deal with this a little bit more deeply later on. So it's kind of like a birthday function. Think about it that way. The negatives don't work for the birthday analogy because there's nobody who's a negative age, but you kind of get what I'm talking about. All right, we're going to leave this alone for now. We've got a few more vocabulary words to work on. So I said 5. We just looked at 2. Let's take a look at this one. Another type of important function that we're going to talk about is the absolute value function. And I'm bringing back this terminology of parent graph because parent graph means a graph that shows us the type of a whole bunch of other graphs. So the parent graph of the absolute value function is f of x is equal to the absolute value of x. The way these graphs always look when they're this kind of function that follow this format is that they will always look like a V. This particular function looks like this. And let's think about why. So I'm going to quickly jot down some terms. Remember, we can always, and I hope you see us using the XY chart or the f of x chart table because it's really necessary. It's really, really helpful. So I'm just going to plug in some numbers. If x was equal to -3, right, if I threw a -3 in there, the absolute value of -3 is 3. If x is equal to -2, the absolute value of -2, is 2. How about -1? You got it. 0, yep. 1, +1. Notice f of x in this case can never be negative because we know that the answer to an absolute value question or question that has or an expression that has absolute value around it could never be negative. So I can keep going on like this for the rest of my life. But I won't. I will spare you. So here we've got at -1, this would be +1. At +1, this is also +1. So that's how we get our V shape. At 0, 0, we're at 0. So far I've graphed these 3. At +2, I'm up at 2, so I should be around here. But also at -2, I'm up at +2. Kind of fixing that. I know my V's a little crooked. You get it? So absolute value functions have this characteristic V shape. This is considered the parent function, and you'll see another example of that a little bit later on. So our final 2 pieces of vocabulary, well, actually really one, because I actually pulled one out. The textbook talks about a piecewise linear function, and I think that's a little bit dubious. It's a little weird because some people, like I was just looking online because I didn't really like the term, and some people were talking about it in one way and other people were talking about it another way. No worries. So a piecewise function is a piecewise defined function is how the text call it. I'm going to call them piecewise functions, period. Is a function defined by 2 or more expressions. So they might look something like this. So f of x is equal to, and it's a whole bunch of stuff. So sometimes f of x is equal to, I don't know, something normal like 2x plus 3. That's just a linear line, but a linear equation. But I only want that as long as x is greater than 0. Right? Weird. But then I could come back and say, well, then I want f of x to equal just x when x is less than or equal to 0. So what I've done, the key here is to look at this part. This gives me the domain in a sense. It tells me what x values I'm going to put in here. I know it seems crazy, but I just wanted to throw it out there. Our example will clear up some of this stuff. Let's get started on some examples. We can probably do 2 and then I'll put the rest on another video. So let's take a look. Let's see what we got. So the first part is we have a greatest integer function situation. Notice this is not like the one that we had before. This should all kind of be attached like that. All right, it's not like the one we had before where it was just an x inside of here. It's actually an x plus 2 in there, right? So we need to kind of find a way to graph this. I know I kind of graphed it quickly when I was talking about the birthday analogy. Don't stress that. I'd like you to really set up a chart. So what you would do is you put your x value here, one part. The next part, you're going to talk about what
what it would be if it didn't have those funky brackets here that made it the greatest integer function. And then you're going to streamline it and put down what the greatest integer function symbol actually does to your number. So we'll put a couple of examples in here. So I'm going to start off with the number 0. 0 is cool. 0 plus 2 is 2, right? So I've got 0 plus 2, sorry about that, equals 2. So 2's here. What's the greatest integer? What if I put 2? What's the greatest integer less than or equal to 2? Well, it's 2. Right? Remember, when I turn 2 years old, I'm 2. That's the age. I'm 2. Right? So let's try another one. What about 0.25? So if I have 0.25, this is going to be x plus 2, or 0.25 plus 2 is going to be 2.25. What is the great? So now if I brought it over here and put it in this section here, I have to figure out what is the greatest integer greater than or equal to 0.25, and it would be 2 again. Get it? If I am 2 and a quarter years, I'm still 2 years old. Even if that's my real age, everybody's going to say I'm 2. And then I can continue that. So I think you guys are getting the fact that, like, if I did 0.75, I get 2.75 here, but it would still be 2 because I haven't turned 3 yet. But as soon as I get to 1 here, 1 plus 2, I didn't have to write that. 1 plus 2 is 3. The greatest integer less than or equal to 3 is 3. And then, so 1.1 would give me 3.1, still 3. So anything from 1 all the way up to 2 is going to give me 3. So when I get to 2, get it? 2 plus 2 is 4. Greatest integer less than or equal to 4 is 4. 2.25. 4.25 in here. What is that going to be? Still 4. You guys get it, I hope. If not, rewind it. Go back to the birthday thing. I think the birthday thing's a good idea. I like it. All right, let me just grab this and stop talking. Okay, so when x is equal to 0, my function says go to 2. So at 0, I'm going to start here at 0. I'm going to go to 2. So that's going to be my first stop. When x was equal to 0.25, I'm still going to come up here at 2. In fact, I'm going to stay at 2 as long as this is 0, 0.25, 0.75. So I'm all here at 2. But as soon as I get to 1, I'm not at 2 anymore. This isn't Kansas. I'm not at 2 anymore. So I got an open circle here because I'm saying this is all gravy as long as x is equal to 0 point something. But as soon as I get to 1, that's my 1 value, I pop up. See, at 1, I go to 3. And so I'm going to start here bold. And everything in between 1 and 2 is going to still map me to 3, right? 1.1. I didn't do a whole lot between 1 and 2. But if I did like 1.5, it would be 3.5, and then 3.5 still gets rounded down to 3. And then so I'd have this. And oftentimes, once you get a few of these steps, you can go through. I know this isn't looking that great. My handle isn't as excellent as I would like it to be. But you can go through and follow the pattern that you have. So that's what we have going on there. Pretty cool, huh? All right, so we graphed it. Now we need to do this other part. We need to state the domain. Remember, the domain means all the x values that make sense in my equation. What are the x values that I can put in here? Could I put negative numbers in here? Absolutely. Actually, I should do a negative number. Wow. All right, let's do a negative number. So I'm going to just add on to this chart a little bit just so we can think through it. Come on, you already know this is going to be 2 videos. So we can just take our time. All right, so what if this were a negative 0.3? So this is a negative 0.3. What is the greatest? Okay, so if this is negative 0.3, then I'm going to add 2 plus negative 0.3, which is going to give me a positive 1 point. What is this, children? Y'all know I'm old. A positive 1.7. Is that right? 1.7. Yeah. So a positive 1.7 when I add 2 plus negative 0.3, 1.7. And what's the greatest integer less than or equal to 1.7? It will be 1. So let's go over here when I graphed it. Negative 0.3 up at 1. Get it? Get it? I hope this is making sense. All right. I don't want to beat a dead horse. That's horrible. So x, the domain, looks like I can put any old number in here. So my domain is going to be all reals. All right. All real numbers. Now my range is a little different. Think about the range. Remember, range refers to my y values. or the values of the function, the values of f of x. Remember, y and f of x